Hello and welcome to helpyourmath.com. In this video, we are going to look at sketching graphs of transformed functions when we're given a graph with no given equation. Before we get to that, let's just quickly review transformations of functions. When describing changes from the given or parent function, we look for three types of transformations. First, shifts in the graph. These could be either vertical shifts, and vertical shifts, we know we're going to have those if we have that function and then there's something being added outside of the function. That's going to move the graph up if k is positive or down if k is negative. There are also horizontal shifts. That would be when there's something happening within the function itself. The graph will scoot to the right if h is positive, and it will scoot to the left if h is negative. We also look for reflections in the graph. We'll know we have a reflection because we see a negative somewhere, so we see a negative attached to the function. If the negative is on the outside of the function, that's going to be a reflection about the x-axis. If it's within the function, we see a negative x inside that function, that's going to be a reflection about the y-axis. And lastly, we look for stretches or shrinks. We see a stretch if there's some constant being multiplied to our function and the absolute value of it is greater than 1. So if we have k times f of x, this indicates to us that the graph is going to stretch vertically. If we have k times f of x and k is somewhere between -1 and 1, so it's a decimal or a fraction, then we will see a vertical shrink. The graph will get more squished together. Let's look at our examples. So we're given this gorgeous function of f of x, and we want to figure out what the graph of g of x is going to look like given g of x is f of negative x. So what does this negative indicate to us? How is this different than f of x? This indicates that we do have a reflection. Because it's happening within the function, that's going to be a reflection working with our x coordinates, which would be indicating it's going to be a reflection about the y-axis. Let's first figure out what the key points are of our graph of f of x. So we have this point here, which is at -4, +1. Up here, I notice we have an open circle at -1, +4. Down here, we have 0, -3, a y-intercept. And here we have 2, -2. So those are the four key points for our graph of f. What we're doing to figure out what the graph of g is we're going to negate the x coordinates. So that means -4, 1 for g would become 4, 1. 4, 1 is over here. Up here, -1, 4 is going to map to, on g, it's going to be 1, 4, and that's an open circle at 1, 4, nice open circle. Down here, 0, -3, wait, there's no -0, so it's going to stay at 0, -3 down here. This would would stay 0, -3, and 2, -2 would now map to -2, -2. And if you know me, you know that I am terrible at drawing straight segments on this screen. So I kind of cheated and had the work done ahead of time, but we would want to connect them with use a straight edge to connect these. And here we have the graph of g of x. So here I have both f of x in blue and g of x in orange, and I drew a beautiful axis of symmetry at x equals 0. Do you see how nicely it reflects about that y-axis? That's what we're looking at here. Okay, in our next example, we have our original f of x, and this time we see the negative on the outside of the function. That indicates it's affecting the y coordinates. So it's going to negate the y coordinates. -4, 1 will now map to -4, -1. -4, -1 is here. -1, 4, our open circle, will map to -1, -4. -1, -4, an open circle there. 0, -3 is going to map to 0, 3, so 0, 3 is going to be up here. And 2, -2 will map to 2, 2. And just to see when we use a straight edge what this should look like, there it is. There's our graph of g of x. Comparing it to our graph of f of x, so you see f of x in blue, g of x is in orange. Do you see the symmetry about y equals 0, that x-axis? Gorgeous. That's what happens when we have this negative in front of the function. Okay, here we have g of x. This time it's -2 plus f of x. What I would do is I would turn this equation around so that way the f of x is listed first so we don't get confused. Sometimes people see the -2 and they assume that it's the coefficient. It's not, because it's being added to f of x. So g of x is really f of x minus 2. This indicates that we do have a vertical shift. This is a vertical shift, and the whole graph is getting picked up and moved down 2 units. It's going to move down 2 units. Moving down 2 units will affect the y coordinates. So let's map out what the new coordinates will be for our graph of g of x. If this is going to move down 2 units, we're going to subtract 2 from the y. We're going to be at -4, -1. So -4, -1 is down here. Here we're going to subtract 2. It's moving down 2 units. That would be -1, +2. We're going to have an open circle at -1, +2. 0, -3. If we subtract 2 from our y, we have 0, -5 down here. And 2, -2. If we subtract 2, we're going to be at 2, -4. 2, -4. Use a straight edge to connect these, and there's that graph shifted down 2 units. Notice that when we graph f of x with it, it's the exact same graph. It's just literally shifted down 2 units. So if you do this and you make a mistake, like if you accidentally subtract 2 from -2 when you have 2, 0 up here, you'll notice that your graph isn't going to look like the given graph, and hopefully you can catch your mistake. This was g of x equals -2 plus f of x. What do we have next? We have g of x equals 2 times f of x. This indicates to me that we're going to have a vertical stretch, so that this graph is going to look stretched out compared to our graph of f. Let's see what happens. This is going to, since the 2 is being multiplied to the function, that's affecting the y coordinates again, all the y coordinates are going to get doubled or multiplied by 2. So -4, 1 is going to map to -4, 2. -4, 2 is up here. -1, 4 will map to -1, +8. We're going to guess where that is, and that's an open circle, probably right around here. 0, -3 is going to go all the way down to 0, -6. And 2, -2 will become graph to 2, -4 in G. So 2, -4. Oops, 2, -4 is over here. And let's look at our nice stretched out graph. There it is. Isn't that stretchy, right? You can see compared to that parent function, it's like somebody took the given function and just pulled it apart, made it taller, stretched it out. We call that a vertical stretch. Okay, you made it. This is the last example. What are we doing here? It looks like, and again, if you want to, you can turn this around so it says x plus 2. This would be a horizontal shift. We have a horizontal shift. In this case, what's happening to the graph? We're going to pick up the graph and we are going to move it 2 units to the left. Be careful when it's inside the function. When it's inside the function, it does the opposite of what it looks like. So this is going to shift left 2 units. And what that means is that every x value, we are moving it 2 units to the left. We are subtracting 2 from it. So each x coordinate, we're going to subtract by 2. This would become -6, +1, -6, +1, because I'm subtracting 2 from -4. Up here, -1 minus 2, this is going to be -3, +4, so -3, +4 is up here. 0, -3, we're going to subtract 2, that puts us at -2, -3, -2, -3. And here we're going to subtract 2, we end up at 0, -2. There's a new y-intercept in town, 0, -2. There's the graph of what the transformed function looks like. There's the original function. So you can see the original function just kind of moved to the left 2 units because that's what x plus 2 indicates to us. So f of x is the blue, g of x got shifted 2 units to the left, everything scooched over 2 units to the left. These have been examples of transformations of functions. Thank you for stopping by.